Welcome everybody and great that you have all joined our presentation. I am Robert van Steenbergen and I'm here together with Matteo Brunetti and Martijn Mes. We are from the University of Twente in the Netherlands and excited to be here at the Winter Simulation Conference 2021. Today Matteo and I will present our network generation tool to implement large-scale networks realistically in simulation software in order to enable multimodal analysis. Well, first we introduce you to the changing supply chains and network simulation. Then we explain the methodology behind our network generation add-on and tell more about the implementation in Technomatics plant simulation. Thereafter, we show two case studies in which we applied the add-on, and we finalize with the conclusions and further research. Let's start with the introduction. Nowadays, supply chains are changing in various ways. Think about the challenges regarding sustainability and the goal of the European Union to reach zero-emission logistics by 2050. Moreover, supply chains not only have to become more efficient nowadays, but also more resilient in case of disruptions. We all have seen that in the past few years. Furthermore, disruptive technological innovations also have become an important accelerator for change. Consider electric vehicles, connected and automated transport, digitalization and synchromodality, and the increasing attention for drone logistics. Although these challenges have been invented already, what will be the actual impact and value of these implementing them into complex supply chains? This requires in-depth analysis for which we need to model changing transportation networks. Matteo will introduce you to the networks and the traffic simulation part.
Thank you for the introduction, Robert. Nice to meet you all. I am Matteo Brunetti, and let's continue with multimodal transportation networks and traffic simulation. So, multimodal transportation networks are networks with multiple modalities, quite simple. Then a subset of multimodal networks are intermodal networks, where the important thing is that we use the same transportation unit, usually the container, for the whole transport route. For example, we might have trucks in the first and last mile, and another modality, barge, plane, train, for the long haul. And then we keep the same container. A subset of intermodal networks are synchromodal networks. And here the idea is that we don't plan ahead which modality to use, but we just give some constraints on the service levels, budget, time window, whatever. And then once for example, the truck with the container arrives at a certain location, like a port, based on the circumstances of the operations at that moment, like a late barge or some traffic, we might decide on a different modality that might fit better our purposes. Now, how do we represent traffic congestion when we think about road transport? That we do with traffic simulation. So we have three main approaches for traffic simulation. Those are macroscopic models, microscopic models, and mesoscopic models. Macroscopic models, you can imagine them as fluids in a pipe network. So it's a more coarse, high level of detail where the traffic flows are aggregated. And that allows us to get statistics on the whole system, like throughput, in an easier way. And it's also easier to implement this type of model. However, it's less accurate. If we want something more accurate, we go to microscopic models, where we have individual vehicles represented, and so we have an accurate physical traffic flow. However, these are computationally heavy, and therefore we usually represent very small areas or a set of intersections, and nowadays computers are getting more powerful, but still they are quite heavy. And finally, we go to mesoscopic models, and that's when we can get a hybrid, and so the proper perks of both worlds. However, these are harder to build. What we do with our approach, we are able, through our add-on, to create flexible models. So it might be multimodal, intermodal, or even synchromodal with some smarter algorithms. Also, we are able to represent multiple modalities and to model a different level of detail, for example, microscopic or mesoscopic. And still, we are able to gather aggregated statistics and also to represent large-scale networks.
Thank you, Matteo. I will continue with the methodology we used for our network generation tool. We followed the idea of Meyer from 2013 and Guttenswager from 2019 to use the open source geographic database OpenStreetMap in order to create complex road networks. Furthermore, we also use railway and waterway data to form an intermodal network. For this, we use an open source API in order to import the data we want in the simulation software. Once the data is imported, we transform it to datasets we can use in the software. For this, we convert the longitude and latitude coordinates to usable x and y coordinates using the well-known Haversine formula. Once these are transformed, we will generate rays in the simulation model by creating individual segments between the nodes of the data in order to form a way that follows the curves of the roads. Once all the ways are generated in the model, those are connected to each other to form a network. To form a network, realistically, all the roads are connected to each other in a specific way, considering one-way streets or multiple lanes at the road segment. Once the network is completed, logistics locations are also created in the network, and these are connected to each other to form an intermodal network we can use and apply experiments with. Matteo will tell us more about the uses of the network and the behavior of the simulation model itself.
So, how do we use this generated infrastructure for multimodal transport? First, we generate some modality sources, trucks, barges, and trains, in this example, and they are, for example, close to the entrances of these logistics areas. Then we input centroid coordinates in a table for each terminal or warehouse. This data is not in OpenStreetMap, but usually logistics areas do have this data because it's quite fundamental to them to know which companies are located in which part of their logistics hub. Then we connect terminals and warehouses to the closest infrastructure segment that they are servicing. For example, a terminal servicing barges and trucks will be connected to the closest waterways and roadways. Then let's move to the modalities driving in this and moving along this network. We modeled for now 7 modalities, which are trucks, automated vehicles, trains, barges, planes, UAVs, and helicopters. UAVs stands for Unmanned Aerial Vehicle. Basically, it can be seen as drones. All of these modalities are actually modeled quite simply, no special traffic behavior. What we model in detail is the road modalities, because we are interested in the effect of the congestion, road congestion. And how we model those can be seen in the picture on the right side. So when a vehicle enters a road segment, a new maximum speed is set, and also the safety distance is set related to the speed. When the safety distance threshold is crossed, then the car following model by Herman and others is activated and will return a deceleration value and again an acceleration value when the safety threshold is crossed again when distancing from the front vehicle. Then when a vehicle is close to a turn or enters the turns, then we have a turn penalty which slows down the speed of the vehicle, maximum speed of the vehicle, based on a percentage of the angle. And that is important because in this complex infrastructure, in cities, in logistics areas, we might have many turns. Therefore, it has a big impact on the road transport.
Let's continue with the implementation. We implemented our methodology in Technomatics Plan Simulation, which is not a typical traffic simulation software package. And we want to stress that our methodology is not limited to any specific software package. In our implementation, we created a graphical user interface in order to simply create the networks. One of the things that are required as input are the GPS coordinates of the area. Furthermore, you can choose whatever road categories and rail and waterway categories you want to implement in the model, and set the average speeds for these modalities as well. Furthermore, you can choose the level of accuracy, such as with a larger area, you can lower the accuracy for computational purposes, and you can also adjust the scale of your network. Furthermore, there is the possibility to implement 3D images and satellite images to improve the visualization effects of your model, which you can also see here in the image below. We show two cases to illustrate the possible applications of our tool. The first case considers the island of Sulawesi in the Netherlands, and the second case considers the port area of Moerdijk in the Netherlands. Those are two quite different examples in which the tool can be applied. The first shows the use of drones and trucks in a large area, about 100 by 200 kilometers, and disruptions occur in specific road elements. And the second case covers a smaller port area, where we analyze multiple modalities and possible congestion effects resulting from the vehicle behavior within the tool. Let's zoom in on the first illustrative case. A heavy earthquake occurred at the island of Sulawesi, and a tsunami followed after the earthquake. This resulted in a large disruption of the infrastructure on the island, and also displaced more than 200,000 people. In this simulation study, we analyzed the humanitarian operations that followed from it, and we model trucks and drones doing the distribution in the area. The goal of the simulation study is to find out what role drones can fulfill within humanitarian logistics operations, and also analyze the stochastic disruptions that occur in the area of the road network and the effect it has on truck deliveries. Furthermore, we can analyze the overarching logistics coordination of trucks and drones in a humanitarian operation. In here we see it in more detail of the city of Palu. We applied as well a validation of the road network in order to find out the accuracy of the network. We modeled a few typical routes in the area, which stretches more than 200 kilometers. And we found out that the deviation in distance only was a few kilometers at the longer distances, which was about 3%. Furthermore, when looking at the time aspect, we saw deviations from less than 2 minutes with an hourly trip. And this is quite accurate for the fact that we modeled a large area with less accurate road network for stretching the whole area.
Let's continue to the second case study, the port of Moerdijk. Here we focus on interlogistics, and this happens between more than 120 logistics players, as you can see in the picture. The port services water, rail, and road modalities, and is now focusing on the idea of using automated vehicles, driverless vehicles, electric vehicles, to move containers between warehouses and terminals, but also to move containers from a pre-gate parking area to the internal area of the port. So external trucks would stop at this parking area, leave their trailers or containers, and these would be moved by automated vehicles. What are the effects on traffic congestion of this? We don't know yet, and we want to study it thanks to our model. Here you can see a detail of the simulation model. As you can notice, the traffic infrastructure and the road infrastructure is much more complex compared to the previous case because there's more detail. It's also a smaller area, so we were able to go into more detail. You can see trucks driving around, a train, and a barge. We also performed some validation, still using the OSM routing tool, and the errors are very negligible. The distance for these routes we tested, the difference in the distance is less than 50 meters, and the difference in time is less than 1 minute. So we're quite happy about that. And now we can move on to the conclusions. This is the end of our presentation. We showed you a flexible model generation approach, which is able to represent different scales, but also level of details of the infrastructure. These models can also represent multimodal networks and intermodal networks, and they are generated by using open source data plus some simple inputs by the user. Our research can support feature studies on a rich VRP, but also on the shift between intermodality to synchromodality, because the first step of creating these multimodal networks, intermodal networks, is already done automatically. So now we can focus on more complex synchromodality studies. In the future, we plan to study uncertainty. Specifically, we plan to study congestion awareness for road transport, but also network disruptions, for example, because of earthquakes, typhoons, flooding, etc. This will then impact our dynamic route and job choice. Thank you very much. We hope you got inspired by our work, and we wish you good luck with your large-scale model generation. Thank you.